All right, welcome back. We continue looking at the impact on parameter estimates of transforming variables in a linear fashion. And in this lecture video, we're going to look at this in the context of multiple regression, specifically with two explanatory variables or regressors. So in this section, we consider the multiple regression model with two explanatory variables given by the following. So y sub I equal to beta 0 plus beta 1 times xi1 plus beta 2 times xi2 plus epsilon sub I going from 1 to n, which is the sample size. As usual, the epsilons, the error terms of the model, are assumed for the purposes of developing the estimators and things like that. They're assumed to be independent and identically distributed with a mean of 0 and a variance of sigma squared, which is unknown. And for purposes of hypothesis testing, constructing confidence intervals, prediction intervals, and things like that, we would typically assume that the error terms are normally distributed as well. Now, the first thing we need to do in a regression analysis is to estimate the model, to fit the model. And we do that by estimating the model parameters, beta 0, beta 1, beta 2, and also sigma squared. Now, as usual, we'll be using least squares estimation, and the resulting parameter estimators are denoted beta 0 hat, beta 1 hat, beta 2 hat for the estimators of the beta parameters, and then sigma hat squared is the estimator of sigma squared. Now, we've seen how to use the matrix representation of the model and the matrix calculations for estimating the beta parameter. In this video, we're going to see how to estimate these parameters using calculator type formulas, a non-matrix representation, let's put it that way. And the reason we're going to do this is because it's going to help us to see the impact of these linear transformations on the variables, the impact that that kind of transformation has on the estimators themselves. And so to do this, let's look at the following list of summary statistics that are used in calculating the least squares estimators of beta 0, beta 1, and beta 2. And so on this slide, we have the sample means of the variables in the model. And so the mean of the response variable y will be denoted y bar. The mean of the explanatory variable x1 will be denoted x1 bar. And the mean of the explanatory variable x2 will be denoted x2 bar. All right, then on this slide, we have corrected sums of squares and corrected sums of products that are used. And so the first quantity here is the corrected sum of squares for the x1 variable, and that is denoted by cap S, subscripted with x1, x1. Then we have the corrected sum of squares for the x2 variable, and that is denoted cap S sub x2, x2. Then we have the corrected sum of products for x1 and x2, and that's denoted by cap S sub x1, x2. We have the corrected sum of products of x1 and y. That's denoted by cap S sub x1, y. And then we have the corrected sum of products of the x2 variable and the response variable y, and that's denoted as cap S sub x2, y. These are the definition formulas for those corrected sums of squares and corrected sums of products. But we also have some shortcut formulas that come in handy, and we'll utilize those. We're going to use both representations. We'll use the definition formulas when we look at the theoretical development, but when we actually do the calculations, it will turn out, at least in what we're doing here, to use the shortcut formulas for doing the calculations, but they are algebraically equivalent. And so you would get the same values regardless of whether you use the definition formulas or the shortcut formulas. All right, then once we have those summary statistics, the least squares estimators of the model parameters beta 0, beta 1, and beta 2 can be calculated using those summary statistics as follows. And now using this kind of a calculation technique, we would calculate beta 1 hat and beta 2 hat first. And then once we have those, then we would plug those into the first formula here to get the least squares estimator of beta 0. And so you can see here how we calculate these. We use these sums of squares, sums of products in a variety of ways here to calculate the numerator and denominator for each of these. And that would give us beta 1 hat. This formula gives us beta 2 hat. And then, as we said just a second ago, then we would plug those in along with the associated variable means to get beta 0 hat. So this is a useful representation because with these representations, we'll be able to see very easily the impact of performing linear transformations on one or more of these variables in the model and the impact it would have on the parameter estimators. And so to demonstrate those formulas, let's take another look at example 3.1, an analysis of the delivery time data, and in particular, fitting a multiple regression model with two explanatory variables. And so in this particular example, you'll remember that we were modeling the delivery time as a function of the number of cases to be delivered and the distance that the delivery person had to walk. And so we had two explanatory variables, x1 and x2. The response variable is delivery time. And so what we're going to do here is we're going to utilize the formulas that we just looked at to calculate the least squares estimators of beta 0, beta 1, and beta 2 in that model. Now, we need the various summary statistics, such as the means, the sum of squares, the uncorrected sum of products, and so forth, in order to utilize the shortcut formulas to calculate those corrected sums of squares and corrected sums of products. And to do that, I'm going to use the means procedure, PROC means, to calculate summary statistics. And I'm also going to, in a data step prior to that, construct some variables that correspond to products of variables and so forth. And so, for example, I'm going to define a variable x1 to be the product of x1 or times x1, or we could just write that as x1 squared. x2 is x2 squared, or I can write that as x2 times x2. x1 is the variable that corresponds to the product of x1 and x2. x1y is the variable that corresponds to the product of x1 and y. And then x2y is the variable that corresponds to x2 and y. And then I would have the card statement or data lines, and then the data set and so forth. And then I would invoke PROC means after that data step. And so you can see here that I'm invoking this. I'm telling it to read the data in the delivery time data set. And then the summary statistics that I want it to report to me would be the sample size, the sum, the mean, and the standard deviation of these quantities. So that's how I get these basic summary statistics, from which I can then calculate the summary statistics needed to come up with the least squares estimators. And so we see that the mean of the response variable y is 22.384. All right, that was provided here. The mean of x1 is 8.76. The mean of x2 is 409.28. All right, so I have those listed here. And then the corrected sum of squares of x1, utilizing the shortcut formulas, would be 1,136.56. The corrected sum of squares of the x2 variable, again, utilizing the shortcut formula for that quantity, is given here. All right, so 2,537,935.04. The corrected sum of products of x1 and x2 is given here. The corrected sum of products of the x1 variable with y is given here, 2473.344. And then the corrected sum of products of x2 and y is given here. So we've got the summary statistics, the corrected sums of products and the corrected sums of squares that we need. And so now we can plug these values into these formulas to get the least squares estimators of the model parameters beta 0, beta 1, and beta 2. And so I'll calculate beta 2 hat first. And that turns out to be, according to this formula, 0.01438488263. Now I'm utilizing as much precision as possible, to reduce round off error when I do these calculations. Beta 1 hat, using this formula, turns out to be 1.615907211. And then I plug those values into this formula for beta 0 hat, and I end up getting 2.341231124. All right. And we can compare those quantities that I've included on this slide as well to the parameter estimates that we get when we run this analysis using PROC Reg. So the intercept beta 0 hat is 2.34123 according to PROC Reg, and that's what I got over here. The parameter estimate for beta 1, so beta 1 hat, PROC Reg reports that as being 1.61591. All right, and so to 5 decimal places, that's what we get here. And then the parameter estimate for beta 2 hat, reported by PROC Reg is 0.01438. And again, that's the same value we get using the formulas that were presented here. Okay, so we know that those formulas work, they're correct, and they're not too hard to use. All right, so let's move on. So next, let's consider linear transformations of the response variable y and the explanatory variables in the model x1 and x2. All right, and so we're going to transform the response variable and then both of the explanatory variables linearly. All right, and so here we see that we're going to denote the transformed variable y by yi star. All right, that's going to be equal to, defined to be a sub y times the original response y sub I plus b sub y. We transform the x1 variable. The transformed version is denoted by x sub I1 star, and that's a1 times xi1 plus b1. And then the transformed version of x2 is denoted by x sub I2 star, and that's defined to be a2 times x sub I2 plus b2. And so in terms of the transformed variables, we can write a multiple regression model. It would look like this. So y sub I star equal to beta 0 star plus beta 1 star times x sub I1 star plus beta 2 star times x sub I2 star, and then plus epsilon I star. All right, now the least squares estimators of the parameters beta 0 star, beta 1 star, and beta 2 star will be denoted, let's see here, beta 0 star hat, all right, and then beta 1 star hat and beta 2 star hat respectively. And then the corresponding estimator of sigma star squared, which is the variance of epsilon I star, would be denoted by this quantity here. So sigma star hat squared. All right. So the goal then is to estimate these parameters and to look at the relationship between those estimators and the estimators of the original model. Now, recall from lemma 3.9.1, applied to this situation, it would tell us that y bar star, the mean of the y star variable, the transformed response, is equal to a sub y times y bar plus b sub y. So again, y bar being the mean of the original response, and then y bar star is the mean of the transformed response. Similarly, the mean of the transformed x1 variable, x1 star bar, is equal to, by limit 391, a1 times x1 bar plus b1. So x1 bar being the mean of the untransformed variable x1. And then the mean of the transformed version of x2 star bar, is related to the mean of the untransformed x2 variable using this linear relationship. And then notice that these linear relationships are the same as these for the variables themselves. And that is perfectly clear based on what we saw in limit 391. Okay, then applying lemmas 392 and 393, we see the relationship between the corrected sums of squares and the corrected sums of products for the transformed variables and their relationships to the corrected sums of squares and corrected sums of products based on the untransformed data according to these equations. All right. And this is going to become very useful in subsequent slides. All right. And so let's look at theorem 396. So consider the simple linear regression model with two explanatory variables, x1 and x2, all right, given here. Let the response variable y and the explanatory variables x1 and x2 be linearly transformed as we've already shown or discussed, all right? So but I'm including that here in the theorem. All right, so then continuing on here, in terms of the transformed variables, the simple linear, and this is actually, that's a typo. The multiple linear regression model has the following form, all right? And so we've seen this as well. And again, to note the least squares estimators of the parameters in this model by beta 0 star hat, beta 1 star hat, and beta 2 star hat. All right, then the least squares estimators, beta 0 star hat, beta 1 star hat, and beta 2 star hat of the parameters in the model based on the linearly transformed data are related to the least squares estimators beta 0 hat, beta 1 hat, and beta 2 hat of the parameters in the model based on the original data according to the following formulas. All right, so beta 0 star hat is related to beta 0 hat, beta 1 hat, and beta 2 hat according to this expression. So a sub y times the quantity beta 0 hat plus beta y over a sub y. I'm sorry, I said beta. This is b sub y over a sub y minus b1 over a1 times beta 1 hat minus b2 over a2 times beta 2 hat. All right, and then beta 1 star hat is related to beta 1 hat according to this formula, a sub y over a sub 1 times beta 1 hat. And then beta 2 star hat is related to beta 2 hat by this formula, a sub y over a sub 2 times beta 2 hat. And so we can see here that we have very straightforward, simple formulas that would allow us to calculate the least squares estimators of the parameters in the model based on the least squares estimators of the parameters in the original model. We could come up with these values without having to have the actual raw data, without actually having to refit a model. right? As long as we have those least squares estimators of the original model, and we know the linear transformations we're talking about, so we know the A values and the B values, then we can calculate these quantities. Okay, so continuing on, the estimated variances of the least squares estimators, beta 0 star hat, beta 1 star hat, and beta 2 star hat, are related to the estimated variances and estimated covariances of beta 0 hat, beta 1 hat, beta 2 hat, according to these formulas. And so you can see here that we've got a little bit more complicated formula here for on this slide, but this is not too bad. The estimated variance of beta 0 star hat involves the estimated variance of beta 0 hat, the estimated variance of beta 1 hat, the estimated variance of beta 2 hat, as well as the estimated covariance of beta 0 hat and beta 1 hat, the estimated covariance of beta 0 hat and beta 2 hat, and the estimated covariance of beta 1 hat and beta 2 hat. All right, and so as long as, again, we have the estimated variances and covariances of the least squares estimators for that original model, we could use this formula to calculate the estimated variance of beta 0 star hat for the linearly transformed variables. Okay, similarly, the estimated variance of beta 1 star hat is written or can be written in terms of the variance, the estimated variance of beta 1 hat according to this formula, and then the estimated variance of beta 2 star hat is related to the estimated variance of beta 2 hat according to this last formula. All right, and then finally, the next slide, we have the three more formulas. So the estimated covariances of the least squares estimators, beta 0 star hat, beta 1 star hat, and beta 2 star hat, are related to the estimated variances and covariances of beta 0 hat, beta 1 hat, and beta 2 hat according to these formulas. And so the estimated covariance of beta 0 star hat and beta 1 star hat is given by this expression. All right, and you can see here that that involves the estimated covariance of beta 0 and beta 0 hat and beta 1 hat. Also, the estimated variance of beta 1 hat and the estimated covariance of beta 1 hat and beta 2 hat. The estimated covariance of beta 0 hat and beta 2 hat is similar. It involves the estimated covariance of beta 0 hat and beta 2 hat, the estimated variance of beta 2 hat, and the estimated covariance of beta 1 hat and beta 2 hat. And then finally, the estimated covariance of beta 1 hat, beta 1 star hat, and beta 2 star hat is written in terms of the estimated covariance of beta 1 hat and beta 2 hat. And so we see here that we can calculate the various covariances between beta 0 star hat, beta 1 star hat, and beta 2 star hat in terms of the estimated covariances and variances of the least squares estimators from the original model, which is based on the untransformed data. Now, proofs of results 1, 2, and 3 above are provided below. Proofs of results 4 through 9 are left as an exercise. And before we move on, let me just again point out that on the previous slide, all right, so we're looking at the estimated variances of beta 0 star hat, beta 1 star hat, and beta 2 star hat. On the subsequent slide, this is where we're looking at the estimated covariances. And so not only are we wanting to know how to calculate the least squares estimators for the model based on the transformed data, but we also need to understand some distributional properties of those estimators, and in particular, the variances and the covariances of those least squares estimators. Okay, so let's prove this result about how to calculate the actual least squares estimators. And so we'll start by calculating beta 2 star hat. And based on the theory of least squares estimation in the context of a multiple regression model with two explanatory variables, we know that beta 2 star hat has got to be equal to this quantity here. And then we can substitute in or replace these with what they're equal to and the quantities they're equal to expressed in terms of the corrected sums of squares and corrected sums of products for the untransformed variables. And so when we do that, we can see that we can factor out an a1 squared times a2 times ay on the top, and on the bottom we can factor out an a1 squared times a2 squared, and then we get some cancellation, and that turns out to be ay over a2 times beta 2 hat. We do a similar type of calculation here for beta 1 star hat. Okay, you can look through that and verify that this actually turns out to be a sub y over a sub 1 times beta 1 hat. And then once we have beta 1 star hat and beta 2 star hat, we can plug those expressions into this formula. So again, based on the theory of least squares estimation for a multiple regression model with two variables, we know that beta 0 star hat would be equal to y bar star minus beta 1 star hat times x bar 1 star minus beta 2 star hat times x bar 2 star. And so then when we plug these various quantities in and go through some simplification steps, then we get a sub y times the quantity beta 0 hat plus by over ay minus b1 over a1 times beta 1 hat minus b2 over a2 times beta 2 hat. All right. So let's then apply this to the special case of standardizing the variables in the multiple regression model. So as a special case of this more general result involving linear transformations, suppose that all variables are standardized. All right, and so again, we have the standardized version of y. So y sub I star is the standardized version of y sub I. So we take y sub I, we subtract off the mean of the y's, we divide that difference by the standard deviation of the y's. Similarly, the standardized version of x1 is x sub I 1 star, and it's given by xi1 minus the mean of the x1 variable, x1 bar, divided by the standard deviation of the x1 variable, which is s1. And then finally, the standardized version of the x2 variable, which we'll denote by x sub I2 star, is defined to be xi2 minus the mean of the x2 variable, x bar 2, and then we divide that difference by the standard deviation of the x2 variable. So we have performed this standardization, all right, and these are linear transformations, all right, and anyway, we can write again, this is a multiple regression model, not a simple linear regression model, but a multiple regression model, all right, and the goal then is going to be to come up with formulas for estimating the parameters in this model in terms of the parameters in the model for the unstandardized variables. And so that's what we're going to do here in corollary 397. So the least squares estimators, beta 0 star hat, beta 1 star hat, and beta 2 star hat of the models of the parameters in the model based on the standardized data are related to the least squares estimators beta 0 hat, beta 1 hat, and beta 2 hat of the parameters in the model based on the original data according to the following formulas. So beta 0 star hat, turns out it's going to be equal to 0. Beta 1 star hat is given by S1 over S sub y times beta 1 hat, where, oh, and I say I've got a little typo here, so I need to clean this up. All right, so I cleaned that up a bit. And so again, beta 1 star hat, which is the least squares estimator at beta 1 star, is given by S1 over S sub y times beta 1 hat. And then finally, beta 2 star hat is equal to S2 over S sub y times beta 2 hat. And in the formulas above, S1, S2, and SY are the sample standard deviations of X1, X2, and Y, respectively. So again, we have expressed the least squares estimators, beta 0 star hat, beta 1 star hat, and beta 2 star hat in terms of the least squares estimators, beta 0 hat, beta 1 hat, and beta 2 hat. Continuing on, the estimated variances of the least squares estimators, beta 0 star hat, beta 1 star hat, and beta 2 star hat, are related to the estimated variances and covariances of beta 0 hat, beta 1 hat, and beta 2 hat, according to the following formulas. And so the first formula here, the variance, the estimated variance of beta 0 star hat is equal to this expression here, this rather long expression. All right, and again, we get this from the previous theorem. It turns out that we can, if we simplify this, what we get is a very simple formula. The MSE for the original model. So this is the MSE from the original model for the based on the untransformed data. All right, we divide that by n, and then divide that whole thing by the sample variance of the y values, the untransformed y values. And so that would give us the estimated variance of beta 0 star hat. The estimated variance of beta 1 star hat is equal to S1 squared over SY squared times the estimated variance of beta 1 hat. And then the estimated variance of beta 2 star hat is equal to S2 squared over SY squared over the estimated variance of beta 2 hat. All right, and then finally, the estimated covariances of the least squares estimators, beta 0 star hat, beta 1 star hat, and beta 2 star hat are related to the estimated variances and covariances of beta 0 hat, beta 1 hat, and beta 2 hat, according to the following formulas. So we have the estimated covariance of beta 0 star hat and beta 1 star hat, given by this expression. This involves the estimated covariance of beta 0 hat and beta 1 hat, the estimated variance of beta 1 hat, and the estimated covariance of beta 1 hat and beta 2 hat. The estimated covariance of beta 0 star hat and beta 2 star hat involves the estimated covariance of beta 0 hat and beta 2 hat, the estimated variance of beta 2 hat, and the estimated covariance of beta 1 hat and beta 2 hat. And then finally, the estimated covariance of beta 1 star hat and beta 2 star hat is given by this expression, which involves the estimated covariance of beta 1 hat and beta 2 hat. Now, we're not going to prove these various results. They follow in a straightforward way by applying the previous theorem, theorem 396, to the linear transformations represented by the standardization here. All right, so let's look then at example 314. All right, this involves the delivery time data. And what we're wanting to do here is to calculate what are called the standardized parameter estimates for that model. And so again, what does it mean for, when we say standardized parameter estimates? Well, those would be the parameter estimates that one would obtain or could obtain by standardizing the variables in the model and then fitting a model based on that standardized data. And as we've seen, we can do that without actually having to go through the process of standardizing the data and then refitting the model. We can certainly do that, all right, but we don't have to. As long as we have the parameter estimators for the based on the untransformed data, we can apply the formulas that we've just seen and come up with those standardized estimates. And so let's first do the calculations using the formulas. And so using these formulas, the least squares estimates of the model parameters beta 0 star, beta 1 star, and beta 2 star that are based on the standardized data would be as follows. So beta 2 star hat would be 0.30131 approximately. beta 1 star hat would be 0.71627. And then beta 0 star hat, we know, would be equal to 0. We don't even have to do the calculation because we know that it's going to be 0. So we can obtain these least squares estimates by utilizing the formulas and the values that we had calculated for beta 1 hat and beta 2 hat based on the unstandardized data. All right, we can come up with these values without actually having to standardize the original data and then refit the model. The estimated variances of the least squares estimators, beta 0 star hat, beta 1 star hat, and beta 2 star hat, calculating using the formulas are as follows. The estimated variance of beta 0 star hat is 0.01763 approximately. The estimated variance of beta 1 star hat is approximately 0.0052573. And the estimated variance of beta 2 star hat is the same value, isn't it? 0.00573 approximately. All right. And then finally, doing the calculations, the estimated covariance of beta 0 star hat and beta 1 star hat is equal to 0, as is the estimated covariance of beta 0 star hat and beta 2 star hat. The estimated covariance of beta 1 star hat and beta 2 star hat is negative 0.004721 approximately. So those are the values for the least squares estimators themselves of beta 0 star, beta 1 star, and beta 2 star. The estimated variances of those least squares estimators, and the estimated covariances between pairs of those least squares estimators, again, calculated without actually having to standardize the data and refit the model. Now, let's look at this analysis of standardized, or look at analysis of the standardized data using SAS PROC Reg. And so again, what we're going to do here is we're going to demonstrate that we get the same results, whether we standardize the data and refit the model using the standardized data, or if we use these hand calculation formulas that we've been looking at. Okay, so the way that we could standardize the data very easily in SAS is to use PROC standard. All right, and so the syntax is we invoke PROC standard and tell it the data set that contains the data we want to standardize. We specify the mean and the standard deviation that we want the standardized data to have. And then we need to output the standardized data set to a new data set. I'm going to call that data set standardized. And then there's a var statement, and we're going to identify the variables that we want to standardize. And so we want to standardize the response variable y, the two explanatory variables x1 and x2. And then just to demonstrate that the data have in fact been standardized so that they have a mean of 0 and a standard deviation of 1, I'm going to use PROC means, all right, to calculate the mean and the standard deviation for each of these three variables. And that's what we have over here. This is the output from that PROC mean statement. And you can see here that the mean of y in the standardized data set is, well, for all intents and purposes, this is 0, right? Not quite, but that's just because of round off, right? So negative 7.1 times 10 to the negative 17th, that's pretty doggone close to 0. At the mean of x1 is also 0, as is the mean of x2. And notice that for each of these variables, the sample standard deviation is now 1 in that standardized data set. So this using PROC standard has accomplished the goal of standardizing each of those variables so that each has a mean of 0 and a standard deviation of 1. Next, what I'm going to do is I'm going to use PROC Reg. I'm going to do an analysis using PROC Reg using that standardized data set. And I'm just going to fit the model as usual. So y equal to x1 and x2. And then I'm going to specify the COV-B option. This is going to produce the estimated covariance matrix of the beta parameters in this particular model. And then as usual, I'm going to restrict the output to only those quantities that I'm interested in looking at. Okay, so I want the parameter estimates table, the estimated covariance matrix for the beta parameters, and then the ANOVA table for the analysis. Okay, and so then the parameter estimates table, we get the estimate of beta 0. So this would be beta 0 star hat. That's 0 essentially, right? And that's what we had determined previously. The estimate beta 1 star hat is according to this analysis, 0.71627. Well, okay, that's what we got there. And then beta 2 star hat, all right, obtained again by fitting a model to the standardized data, 0.30131. And that's what we got using the formulas. All right, and so we see those formulas are working for us. Then we have the estimated covariance matrix, which is produced by the COV-B option on the model statement. Okay, and so in this table, the variances of the variables are down the diagonal, right? So this is the variance of beta 0 star hat. This would be the variance of beta 1 star hat. And this is the variance of beta 2 star hat. And so we can see that these correspond to the values that we calculated by hand using those formulas. So we get the exact same values. The estimated covariance of beta 0 star hat and beta 1 star hat is given by this value, all right, and that's 0. All right, that's what we got also when we calculated it by hand. The estimated covariance of beta 0 star hat and beta 2 star hat is we found to be 0 when we calculated it by hand, and it's empirically equal to 0 in this estimated covariance table as well. And then finally, the estimated covariance of the beta 1 star hat and beta 2 star hat, we calculated that to be negative 0.00427. I'm sorry, 00472, 0.723482. All right, and that is given by this quantity here. So what we see here is that regardless of which method we use, if we standardize the original data and then fit a regression model to the standardized data, whether we do that or whether we use these formulas for the least squares estimates, their variances and covariances, we get the same values. And what the bottom line of this is that we don't actually have to have the raw data in order to calculate standardized regression coefficients. As long as we have the parameter estimates based on unstandardized data, then we can calculate the standardized regression coefficients by applying the formulas that we've looked at. And if we also happen to have a matrix like this, an estimated covariance matrix based on the original untransformed data, then we can use that along with these formulas to calculate the estimated variances and covariances for the standard based on the standardized variables. Finally, we want to show how to come up with the standardized parameter estimates the easiest way possible. And the easiest way possible is just to analyze the raw data, but request standardized parameter estimates from PROC-Reg. And so there's an option in PROC-Reg, in the model statement of PROC-Reg, that we can issue or use to request the standardized parameter estimates. And that option is the STB option. So we want the standardized beta coefficients, essentially, is what that's saying. And so if we issue that option or that request, then it's going to produce in the parameter estimates table an additional column out here to the right that contains the standardized estimates. And so the standardized estimator for the intercept, which is beta 0 star hat, would be 0. This quantity would be beta 1 star hat, 0.71627. And then finally, beta 2 star hat is 0.30131. And those are the values that we got by hand. And those are the values that we got when we analyzed the data, the standardized data, using PROC. And you can see those values here. All right, so when we analyze the standardized data, okay, we got these parameter estimates, and those are exactly the same as what PROC gives us when we request the standardized coefficients using the STB option. All right, so next what I want to do is to look at some SAS. And there are two programs that I've got here that I want to look at, and I'll provide these on the Moodle. But the first program is a PROC IML program. And so this, again, is for example 3.14, the delivery time data set, and we want to come up with these standardized parameter estimates. And so this program implements the formulas given in the lecture slides for obtaining standardized parameter estimates, as well as the variances and covariances of the new parameter estimates, without having to actually transform the raw data and refit the regression model. So in order to, if we don't want to do these things by hand, we could always program it, even PROC IML or R or, really any language. And so let's take a look at this. And so the first part of the program, I'm just creating the data matrices, the data vectors, and so forth, and then fitting the parameter estimates or calculating the parameter estimates. And so we're not going to look at these in detail. One thing I do want to do is just show how to get columns, get the values for each individual variable. All right, and so if you notice here that the X matrix, I'm entering the design matrix, the X matrix, as one whole matrix. All right, and so the second column contains the values for X1, and the third column in that matrix corresponds or gives the values for the X2 variable. And it's going to be useful down below in order to have the X1 variables in their own matrix or vector, and the X2 variables in their own vector. And the way that I can get that very easily is with this type of statement. And so I'm creating a new vector in this case, and it's obtained by taking all the values in the second column of the X matrix. And so when I express with this expression right here, what this does, because there's no index for that first column, or I'm sorry, for the first dimension. These are dimensions. So the first dimension, I've not given an index. It's going to take all of the rows in this case for the second column. Similarly, this statement here is going to take all rows for the third column and put those into the vector X2. And so we'll print those out just to verify that it's done what we thought it was going to do. Okay, then we get into fitting the model. So we're not going to spend any time looking at that. Okay, then we get down here to the bottom of the program. And what we're going to do is perform the calculations to obtain the standardized parameter estimates. And so we need a variety of summary statistics, as we've seen. We need the mean of the X1 vector. We need the mean of the X2 vector and the mean of the Y vector. And so that's how I'm calculating those quantities. We need the standard deviations for those variables. And this is why it's useful to have each variable in its own vector. All right, and then once we have these, then I can calculate using the formulas the various covariances. So this would be the estimated covariance of beta 0 star hat and beta 1 star hat, okay, given by, there's the formula for that. And then we put a format on it with the matrib statement, and then we print that out. And we do the same thing for each of these, all right? And so we calculate the estimated covariance of beta 0 star hat and beta 2 star hat, the estimated covariance of beta 1 star hat and beta 2 star hat. And we also calculate the estimated variances. So let's run that and see what we get. Okay, so I'll go to the top. All right, and so here we printed out the y vector and the original design matrix X. And then we created those vectors containing the individual variables. All right, and so the X1 variable and X2 variable in particular. And you can see if you scroll up and compare that it did what we thought it was going to do. Okay, now we're going to, we're performing the calculations for the parameter estimates for the untransformed data. All right, here I printed out the X prime X matrix, the X prime X inverse matrix, X prime Y. We calculate the parameter estimates for the unstandardized data. And then we have the estimated covariance matrix of the parameter estimates. All right, and we're picking out the variances which are on the diagonal and the covariances which are in the off diagonal. Okay, now we're performing the calculations for the standardized parameter estimates. All right, and so we have these summary statistics that we'll use, and then applying the formulas that were given in the notes, we see here that the estimated covariance of beta 0 star hat and beta 1 star hat is 0, as it should be. The estimated covariance of beta 0 star hat and beta 2 star hat is also 0. The estimated covariance of beta 1 star hat and beta 2 star hat is negative 0.00472072348, which is exactly what we got before. And then we have the estimated variances of beta 0 star. There are two different ways of calculating this as that we looked at. And I'm just, what I'm doing here is showing that you get the same value regardless of which formula you use. And then we have the variance of beta 1 star hat and the estimated variance of beta 2 star hat. All right. And so we can compare these to what we got when we showed it in the notes. And we can also, compare this to what we would get empirically if we were to first transform the data and then analyze that transform data using PROC Reg. And so let's look at the code to look and see what this second formula is. And again, notice here we get the same value for the variance of beta 0 star, regardless of which one we use. So let's take a look at that. And here is the first formula that I'm using to get the estimated variance of beta 0 star hat. All right, it's that rather long formula. But the other formula we had is given here. All right, so the MSE from the model based on the original data, based on the model for the original untransformed or unstandardized data, we divide that MSE by n, and then we divide that whole thing by the square of the standard deviation of the untransformed or unstandardized response variable y. And so, again, what I'm doing here is demonstrating the equivalence of these two formulas. And when we look at the output, you can see that we get exactly the same value. If we go back to the slides, this is the slide that I'm talking about where we had the two formulas for the estimated variance of beta 0 star hat. We have this rather long, complicated formula. All right, and we have this really nice, it simplifies to this nice formula here. Right, and again, you can see here that regardless of which of those two formulas we use, we get the same value. All right, the next thing I want to do is I want to use PROC-reg. And we're going to use PROC-reg to get the standardized parameter estimates. And we're going to do this in a couple different ways. We're going to first do an analysis where we transform the data, standardize the data, and refit the model. And let me just change this then to be more specific. We're going to standardize the data and then refit the model using the standardized data. And then the second approach will be to request the standardized parameter estimates from PROC-reg. All right, so let's take a look. So let me highlight the first portion of code. I'm going to create that data set. All right, and then I don't need to reproduce all of this. We saw that in the notes. So what I'm going to do here is I'm going to do a regression analysis using the standardized data. So again, the first thing I'm going to do here is I'm going to standardize that data set so that these three variables have each have a mean of 0 and a standard deviation of 1. I'll save that new data set out to a data set called standardized. All right, and so let's do that. Let's standardize the data and then run proc means to ensure that each variable has a mean of 0 and a standard deviation of 1. All right, and so that's what we get. Let me see if I can make that a little bit bigger there. Okay, so each variable has a mean of 0 and a standard deviation of 1. And then what we're going to do is we're going to run PROC-reg on the standardized data set. All right, and we'll see what we get. And so we have the parameter estimates. So the intercept beta, this would be beta 0 star hat. Okay, that's equal to 0. The parameter estimate for x1, so that the parameter estimate of let's see, beta 1 star, so this is beta 1 star hat, is 0.71627, and then beta 2 star hat is 0.30131. Okay, so those are exactly correct. That's what we got before. And then notice also that I've requested the estimated covariance matrix for the beta parameters. And when in my ODS select statement, that is one of the tables that I'm wanting to print out. And so when I do that, here are those covariance estimates. And we looked at that in the slides, and we compared those to the values we got by hand. In fact, if we were to, let's see here, let's do something. What we could do is run PROC-IML again, get those values, and then in PROC-reg, all right, what I'm going to do is, since I've already standardized, I'm going to run this PROC-reg again. Okay, so now we have both the output for PROC-reg as well, I'm sorry, PROC-IML and PROC-reg. And so we could, if we wanted to, we could very easily compare these values to the values that we get up here. All right. And then finally, again, if we are now looking at the easiest possible way to get the standardized parameter estimates, the easiest way to do that by far is just to ask PROC-reg, all right, to print those out along with the estimators based on the unstandardized data. And we do that or get that by issuing the STB option on the model statement in PROC-reg. Okay. All right, and so here is the result of that. So we're performing a regression analysis using the raw data, all right? And we've requested the standardized parameter estimates from PROC-reg using the STB option. So we get the original parameter estimates. These are the estimates based on untransformed data, but we also get the standardized estimates out here at the right side of the table. And researchers often like to use these standardized estimates because it allows them to compare the relative impact of the variables in the model on the response. And that's difficult, if not impossible, to do with unstandardized estimates or unstandardized data because of the differing units that are used for the different variables. But what this is telling us here is, and by the way, the units, when we standardize data, the units on the variables are standard deviations, right? Standard deviations for each of the variables. And that is also the unit on the response. And so what the standardized estimates here would tell us is that a one standard deviation increase in the X1 variable results in a 0.71627 increase in standard deviation in the response. Similarly, for the X2 variable, a one standard deviation increase in the X2 variable results in an increase in the response of 0.30131 standard deviations of the response. And so based on this, a researcher would conclude that the X1 variable is impacting the response more than the X2 variable. All right, and that's clearly seen when we look at the standardized parameter estimates. Now, sometimes the word importance is used in terms of impact. I prefer to use impact because the word importance, carries with it other, connotations and things like that. So I think it's better just to think in terms of, and that's what is, I think, typically intended, but we don't want to miscommunicate anything. And so we're looking at, what's the magnitude of change in the response for a one standard deviation increase in my explanatory variables. And that's what these standardized parameter estimates give us. All right, so this concludes what I wanted to talk about regarding standardized parameter estimates. But more generally, again, we started this whole process, this whole topic, by looking at general linear transformations of the variables in the model. And there are other situations where that would come in handy. If you wanted to change the units of one or more of your variables in a model, you can very easily do that without having to have the raw data, without having to refit a model, right? You can use the formulas that we've derived and presented to come up with those new parameter estimates and to know what the estimated variances and covariances would be for those new variables. They're for the parameter estimates that are based on those linearly transformed variables. So that wraps it up, and we'll continue on with the next topic in the next lecture video.